So the next part, we're going to talk about artificial neural network. We're going to answer a set of basic questions on what are artificial neural networks, and the simplest, we're going to use the simplest artificial neural network of Perceptron to illustrate the idea behind a general artificial neural network. And we're going to talk about the networks and some key characteristics, how it's different from others. And we're going to mention why artificial neural network has not been successful until recently. As we mentioned earlier, before deep learning, naive Bayesian and support vector machine has all been shown to beat artificial neural networks in various classification tasks. Okay, so what are artificial neural networks? It's a type of artificial intelligence method inspired by the function mechanisms of human brain. I think we all get that idea already through the news. The AANs are really good at performing pattern recognition, and its power probably cannot be cannot be overestimated in lots of application areas. For example, image processing, computer vision, because the system is very good at gathering features. I think this is one of the major characteristics that differentiate artificial neural networks from other applications. Other machine learning algorithms highly rely on the human engineered features. The system performance is largely dependent on the features themselves. Artificial neural network is able to actually filtering through those features and decide what can be used and to what extent they can be used. So it's definitely a very good approach to machine learning. As I think I mentioned last time, we have a class, a whole course devoted to neural network. So today we only going to actually give intuitions. So to prove or provide evidence to my point that the system learns, artificial neural network learns the features, is when you input to a deep neural network with your pictures, the system will layer by layer and learn different features that can be used eventually for a classification task, whether this picture is a human face or not, for example. It can be shown that the features learned at the beginning of the network, it's lower level features. We see lines, boundaries, and in the middle part, we start to see shapes and, quite consistently. And in the end part of the layer, often you can actually see the complete faces. In text processing, similar, although they cannot be presented so visually, similar ideas applies. So artificial neural network certainly is very widely used for natural language processing as well. So I actually found and included this convolution neural network picture. I think it's very useful not only to explain that there's lots of parts that devoted to feature learning when we recognizing a character. A convolution network is the one that's often used to recognize, understand images. So they go through a feature learning step to actually abstract from lots of raw pixel-wise data points to different layers of features that actually can be put into a feed-forward neural network that's fully connected, and eventually to a softmax layer that can do the classification. This is important. It's relevant to this class because later on we're going to talk about transfer learning. And neural network is very useful for transfer learning. And we're going to come back to this picture when we get to the point where we talk about transfer learning. So in reality, when we implement artificial neural network, it's just a collection of interconnected neurons. And every neuron perform a very simple function. It receives input from the previous layer and dispatches output to the next layer. But with those every single node performing very simple functions, miracle happens in the end. We're going to use, artificial neural network, you can think of it as, many people say it's a black box because we see the input and output internally. How it works is actually very hard to understand. This has been cited one of the drawbacks for artificial neural network, that it has lower interpretability. So this could be a representation of artificial neural networks, input, output, and connected to a black box. So the attribute values I want to mention here is often normalized for different types of neural networks, often a small number, depending on the activation function used in artificial networks, often in the range of -1 or +1 or 1 and 0. The one that we're going to use today to illustrate the idea is a perceptron. Perceptron is the simplest neural network. It has input nodes and it has output node. So this is considered a one layer neural network. When we can count the layers in the neural network, there is not, well, some people count input layer, but I think at this time, most people would stop counting input nodes as a layer in the network. We only count the output and the hidden layer. In this case, we don't have any hidden layer in between. We only have one output layer. So therefore, it is a one layer network. So what does this network node does? It accepts input and have the arcs link the nodes to the output node. And each arc has a weight on it. It can be initialized to random and then learned by the system. And there is often a bias, but in this case, the original perceptron actually call it threshold. So we have a difficult time with terminology here. Sometimes I call it threshold, sometimes other times bias, and also bias can be treated as weight as well. So it's a little bit confusing. But I guess you can forget about that. Doesn't matter. It's just a part of the things that you need to generate the output. So for this perceptron, the output is generated using a sign function. If the input x is greater or equal to 0, then the sign function is going to return a 1. Otherwise, it's going to return -1. So this is our, in this case, it's activation function. It also output to the y directly. So in general, so we just illustrated one perceptron that we're going to use as our example in this lecture. But in general, you will have, for general artificial neural network, you have input layers with many nodes. You can have 1 to many hidden layers with many nodes. And you have output layers with certain number of nodes. The most popular number of nodes in the output layer, depending on your prediction problem. For regression or numerical prediction, you will have 1 node in the output layer most often. For classification task, your output layer is going to have as many classes as you have. although there's other configurations possible. So besides the weight, the weight is connecting node to the next node, to next level's nodes. The nodes may not be fully connected depending on the network topography. But the nodes are often indexed by pairs of, weights are often indexed with pairs of the nodes that it's connected. And bias is to the layer. So there is one bias each layer. And every node has taken those input, and it has activation functions, and it has output. So learning a neural network is just trying to learn the weight and the biases that you put into the network. The network topology was given or chosen by you. And in terms of how many nodes in every layer is all hyperparameters that you need to decide. So you can think of the topology has been given. The learning is just a task of finding those weights. So this is our perceptron that we're going to use as example. To make these things a little bit easier to read, I have converted this T to a weight. So weight now is starting from 0 to D. I admitted the last T, negative T here as the weight with X0 all being 1. So this is equivalent to using T as a threshold. So the rest of the slides here is to illustrate the process of learning the weights. So in general, in neural network learning, you actually initialize the weights with some random numbers. There has been substantial research on how to initialize the weights for the neural network. But some sort of randomization is definitely involved in there because we actually don't know what would be the best thing. The rest of the process steps is to just adjust the weight so that the weight help us to predict our training examples in a correct way. So once we initialize the weight in the simple neural perceptron for every training example, we compute the output function. And then we found how this output function different from our expected result. If we expected -1, but we didn't get -1, then there is an error. And then we're going to, this is the error. So this is our truth, and this is what we predicted. And the difference is our error. So we're going to adjust our weight by adding a little factors to this weight in order to make our function predicts better the next round. So in general, the artificial neural network have a similar learning function where the next weight is a function of the initial weight and plus lambda, that's the learning rate, and the error and the initial input. The general formula is the same, except here we just our function is simpler. So we will do this, update the weight, then we read in another example using the new weight and compute the output and see how this output is different from the given value. We update the weight again until we have completed a certain number of iteration or our performance of the model has reached a certain threshold. And that's when we would stop. I think we already covered this. So using one example to illustrate how does the network learns. So we have, as I said earlier, I modeled that threshold as another weight. So we have x0 all being ones. That's our artificial thing in order to bring this weight into the picture. So we have our function here is this, the sign function. We do a weighted sum of all those input and decide the sign for this value. And our learning rate, lambda, is 0.1. Our weight updating function is given here. So initially we have a random set of weight. We set it to be 0. And then we read in the first examples. The first example is 1100, and our label is -1. So with 1100 input into this network, we need to compute this output function f. So we put the value here. Weight are all zeros, right? Therefore, our y is going to be 0. Then our function outcome, what was our sign function? If it's greater or equal to 0, then the sign is 1, okay? So then in this case, our prediction is 1. So this prediction is different from this prediction. Therefore, we need to update our weight. So the weight is updated this way. Initial weight here is 0 here. So we add lambda 0.1, and our y was -1 minus our prediction is -1. Then we time this x1, that was the original one, and this gives us a new weight of -0.2. So we put it here. And we do the same for the second. For the second weight here. So it was initially 0 learning curve, lambda learning rate. And then so all those are going to be the same for every node that we work on, because the difference, the error was the same. But the initial input is different. So we have 100, so here is 100. So this gives us a new round of weights, and we put this new weights here. And then we read in another example, and using this new weight to compute the f, the function. And we compare this function and find the difference, and we go through the same thing again to update this weight. We will go through this for all the training examples we have. We're going to do that randomly. So we pick a random example, update, pick another random example, update, pick another random example, update, until we completely run through all the training example. That completed epoch. And we do that multiple epochs many times. So you can see that the training process is computationally heavy. And this is our result of the epoch. So after the first, at the initial thing, we have all zeros. After the first epoch completed, we have this set of weights. And we continue and do this until some termination function is completed. So to summarize, the learning process is the process of reading an input example, go through the network. This is called feed forward. So here we only have one node, so still it feeds forward to this output function. If you have hidden layers, the values and the weights help you to fit their value to the next layer. And those nodes will output additional send their output along the way to the next layer until the output layer is reached. And then we compare the system's output function with the truth and find the error and then adjust the weight. When here we only have one layer of weight, when you have multiple layers, the arrows are propagated back. It's called back propagation. So every weight in this network is adjusted for the next example. Okay, question. In this perceptron example, we can see our Wx is a linear combination of the input variables. So that our decision boundary is linear. In general, artificial neural network does not want a linear decision boundary. That's why different activation functions are used. So if you use a linear function, linear function like this for your activation function, your entire network will be only useful for linear separable data. If you use those curvy things, and those things, really, you will have a nonlinear, you can learn approximate any nonlinear and linear functions. And there are various types of neural network that has been used. Single layer network, Perceptron is one example, and versus multi-layer network with m number of hidden layers. Networks, a lot of them are feed-forward, like what we just demonstrated, but some are recurrent network, which means that the information can actually feed back from a later layer to a previous layer. For text processing, the long short-term memory machine is an example. I mentioned before, the nodes in a neural network does not have to be fully connected, but a lot of times they are. So learning the network, I think we actually went through this already. Feed forward is to get to the output and then find the difference and then back propagate the arrow. And we go through this earlier, but the idea of back propagate arrows is a way of minimize. We want to find, we want to minimize the arrow in the direction that would reduce the arrow the fastest. So again, we have a cost function that's non-convex. So therefore, we would do gradient descent to find the global minimum. Find the direction where we want to descend to reduce the arrow. This is a visual. I want to show this very, very quickly. It won't take long. For a neural network, repeating what we just said, it's just a different way of looking at it. So we're going to have initial random weights on all the edges. And then we randomly select one training example. We feed forward and find the output. We compare the output to the real value that gave us the arrow. And we see there's an arrow. We propagate the arrow back onto each layer of the network and resulting every layer's weight being adjusted in the direction that would reduce the overall arrow of the network. So that's the curly thing, the learning curve and the gradient descent technique. So we update the weight, we present another random example. We find the difference, and we again go back and adjust the weight until we have completed a certain number of epoch, or our performance of the network has reached certain things. It's a very, very long process. to train a network. Looking from another perspective, initially say your data points are distributed this way and you have this random set of the weight. Your current network with the initial random set of weight are going to create a decision boundary like this, maybe. That all the things here are going to be considered, predicted as yellow, and all the things above predicted as blue. Then we keep on updating the weights, and then the performance is going to adjust the decision boundary changes. We do it many, many times. If you don't stop it, it will definitely overfit your data and make a perfect prediction. There is also a live demonstration that you could actually play on your spare time. That you can actually generate a different part of the different data sets and see how configure neural network and see how it learns over time. And the concepts in the live demo that I have not covered here in this lecture is batch and regularization. They're pretty basic and important concepts, so I thought I should cover, even though our example did not touch upon those. Earlier we said every one training example going to result in an update of the network's weight, all the weights within this network. But you don't have to do that. So batch is a concept, the number of the training examples processed before you update the weight. We did batch size equals 1, so every one training example processed, we update the weight. But you could actually have other batch sizes. For example, I process every 10 examples, then I update the weight. You could also, in other extreme, I could process the entire training example, then I update the weight. So one epoch actually update the weight once. So there's different way of training. Which way is better? Really, I can't answer that question. It's totally depend on your application. You have to try different ways. Regularization is a technique because artificial neural network can approximate any function. It's as powerful, probably more powerful than decision trees. When we study decision tree, overfitting is a big concern. Similarly here, overfitting is a big concern. So the loss function that we, by the way, loss function is also called objective function. They're all synonyms. What this function does, you can see this is the true result. This is our output, and we found the difference. We want to minimize this, right? But this is a regional loss function that we want to minimize. But in order to prevent the network from overfitting, we would add another term. So this is called regularization. There's two options. One is called L1 regularization. So this just basically the absolute value of the weights. So beta here represents all the weights in the network. L2 is square of the weights. So between these two, so what you can see, the system is trying to penalize because we want to minimize the whole thing. So the system is going to penalize the weight that's too large. The system wants weight to be small and distributed. They don't want the weight that's overly big that overfits certain phenomena. So that's the use of the regularization. I think almost all network use regularization. I think L2 is used more often than L1, and L1 has a special feature that it can, depending on your setup of this lambda, this lambda is actually control this the effect or the extent of regularization. It's not the learning rate lambda. So this lambda depending on this L1 tends to drive certain weights to 0. This, in effect, is similar to that you certainly disabled some features in the network, because when the arc has the weight of 0, and then that information will not be able to pass, the output from that node will not be able to pass to the following layers. So this has the effect of feature reduction. Some applications found feature reduction useful because the feature was really, really messy. L1 regularization helped the system to select features. But majority of applications seems to me that L2 is used more often. So earlier I mentioned that artificial neural network has been studied for a long, long time, at least 25 years since the first time that I heard about it. But it didn't make a big splash until recently. The major issues earlier is when we propagate the arrow back to the network in the backward way. So remember, when we train, when we have a forward process to push the data from the beginning layer to the output layer to get output. When we computed the arrow, we need to propagate that arrow back to update the weight of every layer. This arrow distribution involves the product of multiple layers. So the layer at the very beginning of the network could be very big or very small, because when you take the product of many small numbers, you're going to get extremely small number. That makes the learning rate really, really slow. So the weights at the beginning of the layer almost not updating itself every time a training example passed through. In some other situations, you could have bigger numbers, greater than 1 numbers. When you have lots of those numbers, product of those numbers, you're going to have a very large learning rate, effective learning rate at the beginning of the network. That will make, remember our graph there, you could actually certainly jump over and miss certain important things. So the rate of learning therefore are different in different layers. And we know the earlier layer learns the basic features, that later layer use the basic features learned from the beginning of the neural network and construct more abstract and more useful features. If the learning rate are not consistent, then it certainly hurts the performance of the algorithm, the entire system. It take a very, very long time to train, and it does not provide a very good result. Over time, people have researched different network topology, and there are studies, as I mentioned before, lots of studies on how to initialize the weight for the network to reduce the chance of unstable gradient problem. And the activation functions right now, I think ReLU is probably the popular one, or the leak ReLU, because it has a tendency to reduce unstable gradient problem. Design issues, really there's not much to say, because a lot of those hyperparameters you have to just to try out given your problem. There's typically, if you do image processing, I mean, it's definitely convolution network. If you do other type of analysis, they're probably also well-known and tested neural network topologies, and you should start with those. And then adjusting the hyperparameter, as we have demonstrated and stated before, you can use grid search or random search to find a good combination of different parameters. To summarize, artificial neural network is really, they're universal approximators but could suffer overfitting. For interpretability, I think we also talked about this. Gradient descent, because the objective function is not convex, it could converge to local minimum. You could, by random training examples and run thousands of epochs, with validation might help address this question, but there is no guarantee that you will find the global maximum. And it's not known to you whether you'll find or not find global maximum. You often need a large amount of training example. And even with large amount of training examples, you do that, you do many epoch, so it's very time consuming. Yeah, so next point I mentioned, the building model is very time consuming, but testing is very fast and the performance are often good. So I guess to some extent, it's worth the time to build the model. It learns the feature along the way, unlike other algorithms that we have to provide the feature. If the wrong feature being provided, the system will just not perform. Work well with unseen data. Well, whether something work well with unseen data is really just a matter of a degree. Many about portability or robustness of this learning algorithms are still a very active and open research area that nobody seems to have a very good idea on how to handle. This is also one of the reasons unsupervised methods sometimes would claim that we don't need any training examples and our performance is not so bad, so why don't we just do unsupervised learning? Okay, I'm going to stop here and ask you for questions.
Yeah, I don't know if that's too far, but what is the difference between the recurrent network and the back propagation of the error?
Good question. Back propagation is actually used to update the weights in any neural network.
Yeah. Ah, okay.
Recurrent network means that it changed the feed-forward network. Your input are not just going from layer 1 to layer 10. You actually have circles. Okay. So your input go to layer 2, go to layer 3, come back to layer 2, go to 3, come back to 2.
Okay, thank you.
Yeah, this allows you to memorize some of the things. If you have sequence or dependencies among your input, the recurrent network allows the network to record those information and make use of it.